Okay, now let's continue. This will be the part 30 for General Chemistry 141. We are about, this is the last part for chemical reaction classification and types, concept, everything related to different type of chemical reactions. So we stopped. We're going to take right out for 30 minutes, and the last part, in part 29, we talked about half reaction equations. Now that is for a reaction. The solid zinc metal react with the aqueous hydrochloric acid, produce a ionic compound called zinc chloride, and the hydrogen gas, diatomic molecule, bubbles out from the aqueous solution reaction chamber or reaction beaker, and it become free gas into the atmosphere. So now there are electron transfer involved in that particular problem because the hydrogen in the atom in the hydrochloric acid is +1 as its oxidation state, but when it come out was another hydrogen atom become a diatomic molecule, then the oxidation state for both hydrogen atoms become 0. Alright, we don't know. So there is electron gained from that process. If you gain electron, we consider as what? As a reduction process, reduced, right? And then who lose electron to provide this electron to the hydrogen? The zinc. The zinc starts from 0 as metal because it's a monoelemental species. We consider as metal as a single individual molecule, as elemental molecule, we can call that. And then there is 0 as well as its oxidation state. But then it becomes a zinc chloride as cation in the binary compound ZnCl2. Then that 2+ charge cation, and there seem to be lost 2 electrons from 0. So you lose electron, you subtract, and subtract electrons, negative charge particle, so negative, subtract -2 become positive, right? So that's the positive charge. So these two entities or species, right, and in this process, and apparently play a opposite role or different role in the reaction process. So the zinc lose electron. If you lose electron, we define as what? As being oxidized. So we are able to pick up anything involved in this oxidation process and put them together into a equation we call the reaction, the half reaction equation. In this particular case, we call oxidation half reaction equation. So this is right here. The zinc 0 oxidation state as a solid react with hydrochloric acid by release 2 electrons from its own orbital, and then to become a cation, zinc 2+, and it become aqueous physical state because it's dissolved and dissociated. Right? What is dissociate? Dissociate out of an electron, right? Into the solution and become ionized. We call that. And then so that process is oxidation process. Oxidized, right? The zinc become cation, and then so we call oxidation half reaction equation by losing electron, right? Now to the contrary, the 2 hydrogen atoms, right, by gaining 2 more electrons, where did the electron come from? From the zinc, right? From the zinc. Zinc offer 2. And then just about right, exactly how many electrons 2 hydrogen atoms need. And then add these 2 electrons, all these +1 oxidation state by adding 1 minus, right, -1 electron, and it becomes 0. So they become a 0 oxidation state as diatomic molecule gas, hydrogen gas, and it bubbles out, right? Bubbles out. So that is another half reaction equation we call what? Because the proton is reduced by gaining electron by definition, right? Gaining electron become reduced, we call the reduction half reaction equation. Now in the future, in chemistry 142, if you ever your course can move smoothly to the, I think it's chapter 17, to electrochemistry, and then you were involved this kind of half reaction equation all the time. It's called reduction half reaction equations, and they involve some potential, some kind of voltage involved in the cell. So this is what we're going to talk about in the future. Today we're going to talk about this much, and in the future we'll prepare you to get familiar with that. All right? So that is now these two half reaction equation come from the entire whole, the full net ionic equation, and we can also return to the full net ionic equation by adding them up. Now treat the chemical reaction equations just as treat the mathematical equation, right? The term on the left are equal sign, right? And term on the right equal sign, they are equivalent, so they equal, right? So two expression bridged by an equal sign, that's in mathematics, we call equation. Otherwise we call expressions, right? The left and the right. Now if they are identical and you are able to relate them as identical in mathematical term, it's equal. In chemistry term, it's the direction for the reactants become products. They also can be equal. Now so in this case, we are able to add these two. If you add this thing, and this is what happens is this. The zinc, right? The zinc in this particular case, right? The zinc, right? It's a zero oxidation state solid, right? The metal. And then you add the proton from the hydrochloric acid. You got two of them, right? Alright, and then you got 1 plus charge, its physical state is aqueous. Then these two add up, and then you add these two. Now we're going to cancel them, but we go slow, right? Step by step. So you take down the 2 electron, 1 minus, apostrophe S means plural, now singular. And then you take down this add 2 electron here. Of course they cancel each other, right? So then 2 arrow you can add up. You know, you may make a double arrow. You know, that's exactly up to you. It's exactly same. It's up to you. You know, that's the same meaning, one-way direction, right? Irreversible reaction. Then you add these 2. So you have the zinc, right? 2 plus, right? It's aqueous from what? Zinc chloride, right there, right there. And then you put this down. Add what? Add hydrogen diatomic gas molecule that bubbles out from reaction chamber. So this whole thing is exactly the same as this. You said, no, there's something more. Oh yeah, there's something more, but are they cancelable? Of course. Negative, positive, they cancel. When they cancel out, that's exactly the same as the first one, right? We call it a net ion equation, right? It is from what? From the complete ion equation by taking out the spectator, which is identical on both sides right here. Well, able to cancel them out, right? So treat chemical reaction equation just like a mathematical equation, right? So that's the same thing. Alright, now that's good enough. So we are able to figure out, this way we are able to also figure out how many hydrogen atoms involved, how many zinc and how many electrons. Use those half reaction equation, we are able to balance the redox chemical process or redox chemical reaction. So just like use old-fashioned by counting the number of atoms, which is based on what the law of conservation of mass. Here is counting what? Counting electrons. Now you have how many you lose, how many you gain, and then the number of electrons require how many atoms attached to it, how many atoms receive on the other end, receive these many electrons, and how many atoms, another entity, another species provide this many electrons. So those were determining the coefficient in the balancing equation, just like the old-fashioned, based on law of conservation of mass. This time it's based on what? The law of conservation of energy. You get any idea? So that is what it. Now, it's very. I think I've got enough time. Let's see. All right, 20 minutes. Now let's give you another simple example that we can call a shot for this redox reaction concept we learned. So give you another example. Okay. Another example. Small Alright, so what are we going to talk about? We talk about a steel making process called Bessemer. Now let's in Bessemer process, right? The metal iron, now the Fe, right, solid, right, is extracted, right, from the iron ore, right? Iron ore, what is that? The iron 3 plus, the iron, right, 3 plus 2, right, oxygen 3. Now that's the iron oxide, right, iron oxide. Now that is processed at very higher temperature. Temperatures go, I think they go beyond 1600 Celsius or 1700, because that has to be beyond the melting point of iron. I think the iron is 1590 or something. Alright, at very high temperature. Right? It's way beyond 1600 Celsius degree. That's probably, I don't remember exactly, but I think that's probably around that area. Alright? And then now, so the ore, the iron 3 oxide at very high temperature, it becomes what? Become melted, molten, right? Molten, you know, those iron oxides, and then those cation anion, the electron are free to move around to go through a electron transfer process. You see my point? If the solid is fixed into the crystalline structure or fixed into the solid, you know, structure, it is immovable, right? Immovable. But if you melt it, heat up, and the temperature is high, and then they become mobile, right? Mobile. So they are able to collide each other, and then to exchange the electron to reduce or oxidize each other to have the ions extracted, right? That is, so the reaction is such, right? The Fe2 oxide, right, and the solid, and then in the presence of carbon monoxide, right? Carbon monoxide, and it's a gas, and then going through this process, produce the iron, right? Iron is not solid because temperature is so high. Iron melted, right? It's going to become what? Liquid. And then the second products for this process, Bessemer's process, now world famous, you know. Since that process, we were able to produce a lot of iron, make steel, right? Steel plant, make steel for the industry, right? Of any kind of industry, right? And for the war machine, right? So this is going to be a carbon dioxide gas, right? Produced as a product. Now in this process, of course, we have to double check. It says it's a redox. Now who's losing electron, who's gaining electron, right? Now remember, I said those were solid ore, very, very solid, and they are not mobile until they be melted, heat very high temperature, and they mobile, and the electron and the cation anion will be generated and in the molten salt, and they were able to move around to collide each other and then exchange, and I give you my electron, right? I become oxidized, and you gain my electron, you become reduced. Then that's how reaction occur at high temperature. Now in the old time, we always put a triangle representing extremely high temperature heating for this reaction to occur. right? That's the base, right? So now let's check the is this so first that's so is this redox, right? It's a redox. Redox. So check oxidation state before and after for each element. This one, right? The iron transition metal number 26, right? And can normally have two oxidation states. One is +2 and the one is +3. Now, according to this formula, there's got to be +3 because 3 times 2 becomes 6. 6 times 2, this is 2. This, what, -2, right? Oxygen 99.9% case, a formed compound present a -2 oxidation state, correct? So they have a least common multiple as a 6. So +3. So this is the Fe, right? Fe is iron +3. Oxygen is -2. That makes a neutral, right? Because 2 and 3 right here. And carbon monoxide. Oxygen -2 again, right? -2 again. And the carbon gotta be what? +2. Right, +2. Right, +2. Alright? And this is single monoelemental metal. Of course, we call metal and atoms, but you also can call elemental molecule because it does happen. You can literally get one atom of iron of any metal if it's possible. Use the tools, right? So this is going to be E0. Carbon dioxide. We've been running into this species for several times, and of course, carbon is +4 in this particular case, right? And also recall the position of carbon in the periodic table is what? 4A, right? 4A, and it's only carbon start have what? Have both positive and negative oxidation state values, right? And very unique. Carbon just happen to have +4 and -4 both. Exactly same numerical value, but opposite charge, opposite, on the number line, right? So in this case, this is -2, right? So if we understand that, apparently the iron from +2 or +3 to 0, right? So redox or not, yeah, the iron, right? From +3 become iron 0, right? 0. So how many electrons involved? 3 electrons involved. Right? Each what? Each Fe, I put dash atom. Right? Each one will need 3 electrons, right? And then check the oxygen. Right? The first one is iron, second is oxygen. Oxygen -2, all -2. No, oxygen is not. Oxygen is -2, 2, oxygen -2, right? So, not changing its oxidation state. Right? So that doesn't involve the redox process. Now who involve the redox process? This one, 3 electron, you gain, right? So the gain 3 electron, right? It's gaining 3 electron each. Become what? Reduced. Right? Right? Now here, the last one is carbon, right? The carbon start from what? Start from 2 +2, and then become what? On the other end, as a product, it's +4. So the carbon is +4. So, well, 2 electrons, right? 2 electrons involved. Each what? Carbon atom, right? By losing what? Losing 2 electrons each, right? 2 electrons to be oxidized. Oxidized. So if that is those were understood, right? Then we should have an easy way to write a set of half reaction equations, right? So B, okay, the half reaction equations. Two of them, right? Two of them. So the first one, all right, you have to write this because you have two of them. So each one involves 3 electrons. So 2, so first one, right? 2 iron, right? From what? From 3 plus, right? 3 plus, and then gain 6 electrons because each one use 3, right? 2 of them use 6. Am I right? So you getting what? Getting 2 neutral iron atoms, right, at 0 as liquid. Here is what? Here is solid. Right? You start from the process. That's a solid. And now that's the first one. That is what? You gain electron, right? Gain electron, right? You become reduced. So this is a reduction. Now we're writing half reaction. So that's a reduction. Half. That's a reduction half, right? Reaction equation. Right, that is first one. Then the second one, right? Second one is when we what? Decarbon, right? The carbon. Oh my God, it's dirty. Okay, now the carbon. How many carbon? All right, you got a 1-to-1, but 6 electrons involved. Each one only can involve 2 electrons. You got to have what? You got to have 3. So on the left, you're gonna have 3. So 3 carbon, right? It is what? It is plus 2. A 2 plus as in what? In gas, correct? And then you subtract 6 electrons, right? And give us what? Give us 3 carbon, right? 3 carbon. The 3 carbon, right? It's in gas of carbon dioxide. And that is going to be what? That is going to be plus 4, right? So 6 electron gain lost from 3 carbon atoms, right? Each one lose 2, and all these 3 carbon atoms in a carbon atom in the compound from plus 2 to plus 4. All right, that is. If you add them up, right? If you add them up, all right. If you add them up, all right, then you are able to. But before that, we have to say this. This is going to be what? It's oxidation. Half reaction equation. All right. Now, if you add up, it's going to be what? If you add it up, right? If you add up, let's see, we are able to draw a line to add them up. All right. Add them up. It's going to be the full net ion equation for this process. So you have 2Fe 3 plus, it's in solid, and add 3 carbon and the 2 plus in the gas of carbon monoxide, and then you cancel these 2 electron, 6 electron, right? We don't have space, so you are getting a 2Fe liquid, which is the iron extracted from the ore. We're making steel, right? We're making steel, and then you add what? 3 carbon in the 4 plus, and in what? In carbon dioxide. And the physical state is going to be the gas. Now that is going to be the full scale of net ion equation. Net ion equation for this process we call what? Bessemer steelmaking process. Now, okay, got 4 minutes. All right. So if you have a problem, go over every step clearly, mainly checking the oxidation state change, right? So here is 0, all right. And every superscript with the sign, plus or minus, is clearly, correctly written, and I hope everybody should be able to get it. This is plus 4, let me make this a little bit clearer. Alright, so that will be better. Alright, but if it's of course, either you say plus 4 or 4 plus in the carbon dioxide, and we rather say plus 4 because it is covalent bond, right? It is covalent bond molecule. It does not seem to be ionic. So if the ionic is a 4 plus, in this case we stick around still using oxidation state as a plus 4, right? And that will be it for this. Now, next section, right? What we're going to talk about is going to be part 31. We're going to full scale of stoichiometry. What is stoichiometry? A quantitative analysis of the chemical reaction, and to predict how many reactants required for this process to move forward, and how much products can be produced if the condition of the reaction changes. Basically, the quantity of reactants is enough for, the reactant A is enough for reactant B, or not enough. Then we involve a concept called the limiting reagent concept, and we're gonna get in there and talk about that. Now, we probably will give you one reaction. Now, by the way, this is going to be covered in the final exam, all right? And I will send out, today is a Wednesday, and tonight I'll send out a copy of the last homework, number 10. All right, number 10 homework is including balancing chemical reactions, predicted products based on the solubility rules, or and then write a chemical reaction equation, balance it, and if there are ionic compound involved, and then write a complete ionic equation, and also find a spectator, just like here, complete ionic equation. Find a spectator. If they do have spectator, you can cancel them, and want to fill up those forms, and then those forms are the blanks, right? And then write up the correct net ion equation, and then the last ask you if it's a redox, and then how many electron transferred from who to who, right? That's another concept we already talked about, we're tested, and in the homework as well. And then finally, I want you to write up the correct half reaction equations for both, for oxidation half and for reduction half. Now, but then we go to the quantitative. I'll give you certain number of gram of reactants A react with a certain number of gram of reactant B, and ask you first predict the products, and then predict how much in number of grams and in number of moles of the products can be produced. Of course, if I give you gram, you need to convert the gram into number of moles based on their gram formula weight to compute the number of moles, and then because reaction is based on the mole, it's called a proportionality, right? So time is up, and then we are going to continue the next section, all right? Oh, this last couple seconds. All right.